Welcome to episode 41, Compute Engine for Traditional Workloads, where we explore why virtual machines, or VMs, continue to play an important role in cloud environments. Despite the rise of containers and serverless computing, many organizations still depend on VMs because they closely resemble the servers used in on-premises data centers. This makes them ideal for workloads that need full control over the operating system, specific hardware configurations, or existing licensing agreements. A company migrating its legacy database or specialized application may find that VMs require fewer changes to get running in the cloud. Understanding when to use a VM rather than a newer platform helps ensure the right balance of performance, compatibility, and cost. In this episode, we will learn how Compute Engine supports traditional workloads efficiently and securely while still providing modern cloud benefits. When organizations begin their cloud journey, the easiest first step is often a lift and shift approach, which means moving existing systems to the cloud with minimal change. Compute Engine makes this practical by allowing administrators to create VMs that match the specifications of their on-premises servers. This reduces the complexity of rewriting applications or refactoring architectures. For example, a financial company running an older accounting platform can move it to a virtual machine and maintain the same configurations it used in the data center. The result is faster migration with less risk. However, lift and shift should be seen as a transitional stage, not the final goal. Over time, workloads can evolve toward more cloud-native architectures, but Compute Engine provides a stable and reliable foundation during that transition. One of the most important choices when deploying virtual machines is selecting the right machine type. Compute Engine offers several predefined types designed for different performance profiles. General-purpose machines balance cost and resources, making them suitable for most workloads. Memory-optimized machines provide large amounts of random access memory for data-intensive applications such as in-memory databases. Compute-optimized machines offer high processing power for analytics or scientific modeling. Choosing the right type matters because it directly affects both performance and budget. An organization running a small website might waste money using compute-optimized machines when general-purpose types are sufficient. Understanding these distinctions helps teams match resources precisely to workload needs. Beyond predefined types, Compute Engine allows the creation of custom machine types for even greater control. This means developers can select the exact number of virtual CPUs and the amount of memory rather than relying on preset combinations. Customization reduces waste because resources are tailored to what the application actually uses. A web service that peaks at moderate CPU load but consumes little memory, for instance, can be configured accordingly to save costs. Right-sizing tools help monitor usage and suggest adjustments over time. Many teams start with over-provisioned VMs for safety, but regular right-sizing ensures that spending aligns with real demand. This flexibility is one of Compute Engine's most practical advantages for managing traditional workloads efficiently. Persistent disks are another key building block in Compute Engine. They are virtual storage volumes that attach to VMs and retain data even if the machine stops or restarts. Standard persistent disks use hard drive technology and are economical for large, sequential workloads. Balanced persistent disks offer a middle ground between performance and price. Solid-state drives, or SSDs, provide high performance for databases or transactional workloads that require quick read and write operations. Administrators can resize disks or take snapshots without downtime, giving them flexibility for scaling or recovery. Selecting the right disk type helps control cost and performance outcomes while ensuring the durability needed for critical applications. Local SSDs provide another storage option, but they come with different trade-offs. Unlike persistent disks, local SSDs are physically attached to the host machine, which gives them extremely low latency and high throughput. This makes them ideal for temporary caches, processing pipelines, or workloads needing rapid access to data. However, they are not durable. If the virtual machine is stopped or migrated, data stored locally is lost. Therefore, developers must design applications to handle that volatility, often by combining local storage for speed with persistent disks for reliability. Understanding this balance allows organizations to optimize performance without sacrificing data integrity or recovery capability. Images, snapshots, templates, and golden builds help automate and standardize how VMs are deployed. An image captures a full operating system and configuration, so new instances can be created quickly with identical settings. Snapshots record the state of a disk at a moment in time and are used for backups or rollback points. Templates define reusable instance configurations that simplify scaling. Golden images go one step further by embedding security patches and approved software, ensuring consistency across environments. For example, a healthcare company could create a golden image that includes all compliance tools before deploying new VMs. These features combine to reduce manual setup and improve operational reliability. Managed instance groups simplify large-scale deployments by automating how multiple VMs are created and maintained. They ensure that all machines share the same configuration, making updates and scaling predictable. Autoscaling adjusts the number of instances based on demand, while health checks automatically replace failed machines. For example, an e-commerce platform could increase capacity during a sale and scale back afterward without human intervention. This approach maintains reliability and efficiency even as workloads fluctuate. Managed groups are particularly valuable for traditional workloads being modernized because they introduce automation without forcing a complete architectural rewrite. Load balancing in Compute Engine distributes network traffic across multiple VMs to maintain responsiveness and uptime. Several options exist, from simple regional balancers to global systems that handle millions of requests per second. These services monitor health and direct users to the nearest or healthiest instance automatically. Imagine a global retailer using a load balancer to route customers to virtual machines located closest to their region, reducing latency and improving experience. Without load balancing, a single machine could become overwhelmed or unavailable, leading to downtime. Proper configuration ensures that resources remain utilized efficiently and that applications remain resilient under varying demand. Live migration is one of Compute Engine's distinctive strengths. It allows Google to move running virtual machines between hosts during maintenance without interrupting workloads. This means users experience consistent uptime even when hardware or software updates occur behind the scenes. For administrators, maintenance windows can be planned with minimal disruption, and critical applications keep running. It is important, however, to design workloads that tolerate momentary pauses or network changes during migration. This feature exemplifies the cloud's promise of continuous service while shielding customers from much of the underlying complexity of physical infrastructure. Security remains fundamental for all virtual machine deployments. Compute Engine provides shielded VMs that protect against firmware and kernel-level tampering by verifying integrity at boot time. Encryption keys can be managed by Google or by the customer, giving control over who can access sensitive data. These features safeguard against threats that traditional servers often faced, such as rootkit infections or unauthorized modifications. Administrators can enhance protection further by applying least privilege principles and ensuring service accounts have only the permissions required. Security in Compute Engine is built from the ground up to maintain trust and compliance across environments. Networking is another essential layer of virtual machine design. Compute Engine operates within virtual private clouds, or VPCs, that segment resources into secure, isolated spaces. Tags and firewall rules define how traffic flows between machines and networks, while service accounts authenticate applications securely. For instance, a development VPC can be isolated from production, reducing the risk of accidental access or data exposure. Properly designed network structures support both performance and security goals, allowing teams to grow their environment safely. Understanding VPCs and identity configuration is a core skill for anyone managing Compute Engine workloads. Cost management is a practical consideration for every cloud deployment. Compute Engine offers multiple tools to keep expenses predictable. Schedules can automatically shut down non-essential machines at night, while committed use discounts reward long-term resource planning. Recommendations within the console highlight idle resources and suggest optimizations. For example, a marketing team might run campaign servers only during business hours to cut costs in half. Tracking usage patterns and applying these controls helps ensure that the flexibility of the cloud does not become a budget challenge. Financial discipline complements technical skill when running traditional workloads efficiently. Using virtual machines intentionally means treating them as one of several tools in the cloud, not the only one. Compute Engine excels at supporting applications that still depend on full operating system control, but it should be chosen deliberately based on workload needs. As teams modernize, some systems may transition to container or serverless models, while others remain stable on VMs for years. The key is to align architecture choices with business goals and technical realities. Understanding Compute Engine empowers professionals to make thoughtful, informed decisions about performance, cost, and long-term sustainability in their cloud environments. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.